All right, we're going to look at an example problem of how we can use Gauss's law to sort of look at the electric field in a space, in a region of space, given charge or in charge distribution within that region. So our problem reads, a thin spherical shell of radius A has a total charge Q distributed uniformly along its surface. What's the electric field outside? What's the electric field inside that charge Q? All right, so let's make sure we understand the problem by drawing a picture. So we have this shell, right? So it's a spherical shell, right? So you can imagine it's kind of got a thin wall. I'm kind of slicing through it. And we'll just say this, it's got charge evenly distributed, where the total charge evenly distributed is Q. Okay. Now when we want to look at the electric field inside the sphere or outside the sphere, we're going to take into consideration how can I determine it and what shape can I use that makes my calculation of the electric field using Gauss's law convenient. So I have this sphere. Well, I'm going to use a spherical shape to look at the Gaussian relationship. So if we imagine that we take a sphere that goes around the shell itself, now what have I done? I've taken a surface, a Gaussian surface of a sphere, and I've enclosed a charge inside. And we know by Gauss's law that the flux is equal to the enclosed charge over epsilon naught. And so if I want to determine what is the electric field across this surface, well, my electric field times my area of that sphere is equal to Q enclosed over epsilon naught. And what does that give me? Well, for a radius that is much larger than A, so really far away, let's imagine, this leads to kind of what we did in our example, 1 over 4 pi epsilon naught Q over R squared, which is KQ over R squared. So that should look awful familiar. Using the idea of a uniform sphere, we can very quickly determine the electric field in this space far away from the sphere itself. So where the radius of the sphere is, where the radius of my Gaussian surface is much larger than the radius A of the sphere. Ooh, got a little confused there with my R's and my A's. All right. So we've chosen the electric or the Gaussian surface to make the calculation convenient. That's really helpful because I can take the integral over a known shape. What about on the inside? How is the electric field on the inside? Now we're going to take the same shape of this ring, this shell, and if I'm interested in the electric field on the inside, then I want to put my Gaussian surface on the inside. And what's another shape? Well, if I make my Gaussian surface a sphere on the inside of my spherical shell. Okay, what do we notice right away? Well, there is no enclosed charge. Nothing's inside that Gaussian surface. And so if there's no enclosed charge, this implies there is no flux and therefore no electric field. And this actually gives rise to something really valuable for us. It tells us that inside a surface where charge is distributed on that surface, there is no field. No field is inside this enclosed area. This is really important. This shields us from electric fields or equipment from electric fields. If I can get really sensitive equipment inside of a surface that's charged, I have no charges. I have no electric field on the inside. My equipment is safe. I am safe on the inside because there's no electric field lines inside that surface of an enclosed space. So, kind of a way that we think about how that gives rise to the fact that there's no field inside of an enclosed surface. And we can use, with the way that we use Gauss's law in terms of we identify the Gaussian surface that allows us to make the calculation, allows us to do the integration, especially at this introductory level. Typically, we're going to pick easy shapes like the sphere, and we can use it to calculate the electric field. All right, good job.